So in this video, what we're going to do is use the law of cosines to solve a side angle side triangle. So what I suggest when you're solving a triangle is that you draw a picture of a triangle. It doesn't need to be to scale. It doesn't need to have the angles drawn correctly. Just give yourself something to look at. So I'm going to draw in a triangle, or try to draw in a triangle. And I'm going to label the angles A, B, and C. And then I'm going to go ahead and label in the information that I'm being given. So they're telling me that B is 40 degrees. So this angle right here with cap B is 40 degrees. Side C is 32.5 feet. So side C has to be opposite angle C. So side C is over here at 32.5 feet. And I'm being told that side A is 10.5 feet. So I label in side little a equals 10.5 feet, opposite angle A. And then I know I need to solve the triangle, so I'm going to need to find all of the unknown pieces. And there's some real subtlety to the law of cosines solution process. And so we want to make sure that we're really careful as we walk through this, especially when we get to the second step in the solution process. But we have side lengths A, B, and C. We know A, so A equals 10.5 feet. We don't know side little b. That side's unknown, so we're going to have to approximate it. We do know side length C. Side length C is 32.5 feet. And we're going to need to solve angles A, B, and C. We've been given angle B is 40 degrees, so we'll need to approximate angles A and C. And we know in this case that the law of cosines is the tool to use, because we have an angle but we don't know the side opposite the angle. When we use the law of sines, we need to have an angle and the side opposite an angle in order to be able to do the solution process. So the law of cosines just says, hey, take the side that you don't know and square it. So you get b squared equals, and then it's going to be the sum of the squares of the other two sides. So a squared, it'll be a squared plus c squared, the two sides that I know. Unknown side squared equals the sum of the squares of the known sides. So it looks like the Pythagorean theorem, but because it's not a right triangle, there's a tweak factor on it. It's 2 times the product of the sides that you know times the cosine of the angle that you've been given, so cosine of 40 degrees. Or I'm labeling it in generically, so I'll go cosine of B in this case. The one thing to be careful about, because the angle that we've been given is in degrees, you need to make sure if you're using a handheld calculator or a computer algebra system that you've set that system to degrees instead of radians, or if you have something like GeoGebra where it's going to default your output in radians, you might need to convert your result into a degree measure. So it's just a matter of loading the formula. So we get b squared equals a squared is going to be 10.5 squared plus c squared is going to be 32.5 squared minus 2 times a, but a is 10.5, times c, but c is 32.5, and then it's times the cosine of 40 degrees. And then this is just a number. There's no unknown sitting on this side, so we take the square root of both sides. And taking the square root of both sides will cancel the squaring on the b. We don't do a plus or minus in this case because we're calculating the side length of a triangle, which isn't going to be negative. It's always going to be positive, so no plus or minus the square root. And then if we crank this into the calculator, making sure that we're set in radian mode, when I did this beforehand, I carried it out to 25 point, and it was 370744. And what I'm going to do is carry this out to, because I'm rounding, I'm going to carry it out to 6 decimal places because I'm rounding an intermediate step. But when I approximate my answer up here, I'm only going to round to the nearest tenth because my numbers have been given to me in tenths. So up here I would report this as 25.4 feet, But to minimize the rounding error that I introduce into my calculations, what I'm going to do is carry this all the way out 6 units in my next calculation. So I get B here is about 25.4 feet. And the key is, once I have this, now I have an angle and the side opposite an angle. I have an angle and the side opposite it. So I'd like to use the law of sines. So in other words, I'd like to go sine 40 degrees over my 25.37. I want to carry it out 6 decimal places, 370744. I'd like to do this equals sine of something over the side opposite that something. I'd like to use the law of sines because it's a simple calculation. But I have to be careful when I do the law of sines, because I'm going to wind up having to take the sine inverse of both sides to find my angle. And we want to remember that the sine inverse, when we feed it a ratio, it outputs an angle between negative 90 degrees and 90 degrees. And that's all that it can do. If I'm working then with a right triangle, it's only going to give me an angle between 0 and 90 degrees. And the issue with this is that if the angle I have is obtuse, the sine inverse function isn't going to give me that angle. It's going to give me the supplement of it. So remember, the sine inverse is going to generate solutions in supplementary pairs. So what I don't want to do is put an obtuse angle in here. I don't want to put an angle that's greater than 90 degrees into the sine function, because then when I take the sine inverse of both sides, I'll get the supplement of it. In other words, if I'm solving for an angle and that angle happens to be 100 degrees, which is obtuse because it's greater than 90 degrees, the sine inverse function would give me an 80-degree angle. It would give me the supplement of this. So the sum of the two angles need to add to 180 degrees. The sine inverse function is going to give me the supplement, and I would have to subtract this angle from 180 to get the angle I want. So I don't want to feed, if I'm going to use the law of sines, I don't want to, if I can avoid it, I don't want to feed an obtuse angle in here. So the idea is this. It's really simple. You look at the triangle, and one of the 3 sides is going to be the longest side. And an obtuse angle will always be the angle opposite the longest side on the triangle. So if this triangle has side lengths 10.5, 25.4, and 32.5, the angle opposite the longest side, if there is an obtuse angle, that's going to be the obtuse angle. And a Euclidean triangle can only have one obtuse angle. So if one angle is obtuse, the other 2 must be acute. So what I don't want to do in this case, I don't want to do sine C over 32.5. I might get myself in trouble if I do that. So I'm going to pick the angle that I know has to be an acute angle, right? The side opposite A is a really short side, much shorter than 32.5. Angle A is an acute angle. So I'm going to feed it this ratio right here. And then I just multiply both sides by 10.5 to get the sine of A by itself. And then I take the sine inverse of both sides, which will isolate the angle A over here. And then I'm going to approximate my angle A in the calculator. And when I did that, I got 15.4 degrees. 15.4 degrees right here. And now I have my last angle to get, so I'm going to take 180 degrees, because the sum of the angles of a triangle have to add up to 180. I'm going to take 180 degrees minus my 40 degrees plus my 15.4 degrees to get my final angle. And when I do this, I get 124.6 degrees. Now, what would have happened if we had made the mistake of feeding the angle C into the law of sines? So let's take a look at this. So if I did that, if I did sine 40 degrees over my 25, we used the 25.370744. I used that side length out to 6 decimal places. Had I fed it the sine of C over 32.5. We would have multiplied both sides by 32.5. Let me get this out of my way. So that would have isolated the sine of c. We then would have taken the sine inverse of both sides, so sine inverse of this big mess over here, and that would have isolated the c for us. And then we would have found that c is approximately, when I did this, it was approximately 100, let's see, did it, oh, right here I got 55.4 degrees is what the calculator gave me. So it gave me an acute angle. Again, the sine inverse function is always going to give me an angle on this interval. And then the issue is, what you see is that isn't the angle that you need, but if you do 180 degrees minus 55.4 degrees, you actually do get the 124.6. So the sine inverse function is giving me the supplement of the angle that I actually need. And that's why I went with the angle A in my calculation, because I knew it was an acute angle.